this picture is showing you down here is we averaged across all the evolved arms and said on average what was the length of the first phalanges, the length of the second phalanges, and the length of the third one. The dotted line shows what the length actually is in the fixed body plan. So it's not that, for example, there's some hidden morphology out there that we didn't expect, which is just make all the fingers twice as long. Okay? Of course, our evolved morphologies would then have done better than the fixed morphology. All of them hover around the actual fixed morphology, but there's slight changes through the evolutionary process. So it's actually not the end product that matters too much, but the fact that it's able to slightly alter these morphological parameters as it's evolving this object manipulation. That matters. Okay? So we're not cheating here. Turns out it's the same thing with the radii. It tends to have more or less the same settings overall as the fixed body plan. Same thing for the spacing. It tends to come up with a uniform distribution of fingers around the hand. This is a plot showing, again, remember we could evolve none of the morphological aspects, 1, 2, or 3. We then tried out the evolved morphologies and fixed morphologies on situations where we changed the target size. So new environments that it hadn't seen before. It tends that if you evolve more aspects of the morphology, it's more robust. The absolute difference is not very much, but there's definitely a statistical difference there. So not only do we get these evolved solutions more often, they're more robust. I also lesioned out sensors, so turned on and off sensors in the evolved solutions. The evolved body plans tended to be more robust to that than the fixed body plans. Okay, let's switch to the last line of evidence now. As I mentioned, what we're going to do is either start with our quadruped or start with a prone posture and gradually transition through a number of developmental trajectories up to the same body plan, this quadrupedal body plan. This particular method we've developed we refer to as morphological scaffolding. Somebody mentioned scaffolding already today. Scaffolding is the idea, obviously, that you ease the task environment for the learner. They get the idea of the task, and then you gradually make the task more difficult, and the learner hopefully tracks that change in difficulty. So basically what's happening here is by changing the body plan of the robot over time, the robot's body plan itself scaffolds the learning task. That's different from traditional robot shaping or scaffolding where you're making some change in the external environment. Right? We could have started by putting the object right in front of the robot. It's not hard to move towards the object, it's already there. And then as it learns to do that, we gradually move the object further away. That's the traditional idea of scaffolding. Here, it's the robot's body itself that's scaffolding the behavior optimization process. So let's look at the case without morphological scaffolding. This is an evolutionary run right at the beginning. So it's evaluating random solutions. You can see, obviously, they're not very good. It doesn't get anywhere near the target object. This goes on for a number of hours until things start to improve, and eventually after a couple of hours, you tend to see something like this. You'll notice, it's hard to see, I guess, in this small video, the gait is not quite rhythmic. There's a little bit of noise there, so it's not very robust to external perturbations. In the case of morphological scaffolding, all the regimes start the same, which is that we start with this prone posture. They're also obviously not very good. These are random controllers that we're downloading onto our simulated robot. You'll notice that it just moved and ran away to the right. Okay? So already within a few seconds, we're starting to get partial solutions. It's already figuring out how to orchestrate its limbs. That's interesting. Okay. Okay, let's carry on. Try not to make everybody seasick here. Okay, so again, as I mentioned, after the first phase, after about 20 minutes, we get a robot that's able to locomote towards the block when it's prone. The dotted line here represents the height of the center of mass of the robot. So in this first phase, it's prone. It starts with its belly on the ground and ends with its belly on the ground. We then change the developmental process, so now it starts with its legs flat and gradually there we go. Thank you. Gradually starts to increase or heighten its center of mass, so it starts prone. This is an external forcing, so we are doing this. While the legs are gradually deflecting, the controller is still orchestrating the movement of the legs, okay? So we are enforcing the developmental trajectory here. Once we get a controller there, we move on to splayed, then to upright, and then finally upright to upright, okay? And as I mentioned, I'll show you some results in a moment that